Thank you very much, and thanks to everyone for coming. Today I'd like to talk about how we can use motion to understand objects in the real world. The dream of robotics is to create robots that can interact with us in our daily lives. However, the reality of robotics today looks more like the picture that you saw on the left, where robots are confined to operate in very controlled environments. One reason for this is that most perception methods for robotics today assume that objects in the world are well separated with minimal occlusions and good lighting conditions. However, the reality of the world looks more like this, where objects face heavy occlusions, where objects can be in front of or behind other objects, like the group of pedestrians on the top, and this can create a confusion for most perception algorithms. Objects can be in contact with each other, and there can be poor lighting conditions. Our insight into dealing with these challenges is that the world that we encounter isn't just a still image. We are able to move throughout the world and observe how the world changes over time. So we are able to observe occlusions as they occur. We can observe objects as they come in contact with each other. And we can view the scene as the lighting changes. Similarly, people don't learn about the world just by staring at a collection of images. We learn about the world by moving about our environment and observing how the world changes over time as we interact with our surroundings. So what I'd like to do is show how we can build models that capture how the appearance of an object can change over time. To put this in context of some previous work, I'd like to study the motion of objects at the object level of semantics, as opposed to some previous work that studies the motion of individual points or segments of an image. I'd like to study motion at the level of the whole object. Additionally, I'd like to build models that tightly integrate appearance and motion together, as opposed to some previous models which process each frame of a video independently, and then does some post-processing to link these frames together. I want to build models in which the appearance and motion are tightly linked together at the object level. Now, why is it so important to study motion at the object level? Here's an example to help illustrate this point, and if you haven't seen this before, it probably just looks like a bunch of white and green dots. If we add some motion, then we get a little bit more information, but we probably still can't really make sense of this. However, if we look at motion at the level of the whole object, now we can finally understand what's going on in this image. So the next question is, how do we study motion at the object level? To do this, I'm going to introduce an idea that I call causal appearance reasoning. We'll observe an appearance change in the world, and then we want to model the causes behind that appearance change, which are in this case motion and deformations, because the person has changed their pose. And there can also be lighting changes or occlusions. So in general, we want to observe an appearance change and model the causes behind that appearance change. People can do this very naturally. So here there's a collection of objects, and we can infer that these objects all differ from each other because they've undergone some type of rotation or scale change. Here's another collection of objects, and we can infer that these objects have all undergone some type of structural change. And finally, here's a third collection of objects, and we can infer that these objects have all undergone some type of deformation. And we can do this despite the fact that all of these objects share similar low-level features, which are namely black lines or curves. So we'd like to view an appearance change and model the causes behind that appearance change, and thereby capture how the appearance of an object can change over time. I'm going to show this idea in the context of autonomous driving, but it can be applied to other robotics applications as well. Next, I'll describe the perception pipeline that we use at Stanford for autonomous driving. We receive as input a stream of 3D data, like you see here, and the first step is to process this data to find the different objects in our environment. For each of these objects, we can track it over time and then estimate that object's velocity. The result will then be sent to other modules that can perform classification or planning. Based on my experience working on autonomous driving at Stanford, I've found that these three problems of segmentation, tracking, and velocity estimation are three of the biggest challenges facing autonomous vehicles. And so this is where I focus the majority of the work for my Ph.D. And I've also interned on the self-driving car team at Google, which has further influenced my research decisions. And for each of these areas, I'm going to show how we can model the causes behind an appearance change to give big improvements to our perception capabilities. I'll begin by describing my work on segmentation. Unfortunately, I won't have time to explain all of the methods in detail, but you can ask me for more details at the poster session. So the problem here is, given a collection of 3D points that were recorded with our 3D sensor, we want to process these points and find the different objects in our environment. So we want to be able to say that these points that we've colored in green are all one object. This other group of points that we've colored in yellow belong to a second object. And we want to process the rest of the points to find the other objects. So the points in black are the background. And we're going to do this using a three-step approach. We will first obtain an initial coarse segmentation of the scene. Next, we will watch how the segments move over time. And finally, we will re-segment the scene using the information that we've learned. So previously, we might have over-segmented this car into multiple pieces, but by watching how the car moves over time, we can determine that this is actually just one object. Additionally, we might have previously lumped these people together in this crowd because they're standing very near each other, but by watching the people over time, we can find each individual person in this crowd. Next, I'm going to show how we can track objects over time. So the problem here is, given a sequence of frames and a label in the first frame of some object that you're interested in, we want to find that object in all of the remaining frames of the video. And the way that we're going to do this is, at a high level, we're going to train a neural network to learn the relationship between an object's appearance change and its corresponding motion. Using this, we can then use our neural network to track a variety of different types of objects as they move. Next, I'll describe my work on velocity estimation. So imagine that you're a car driving down the road, and then we eventually will see this car on the right start to pull out into our lane of traffic. And in response, we need to slam on our brakes. So in order to operate in this environment correctly, we need to be able to estimate that this car on the right is moving at some speed, this other car that we were following was moving at some other velocity, and this third car on the right is stationary, so we don't really need to worry about it. So to estimate the velocity of all of the objects that are around us, I've created a novel method that captures how the appearance of an object can change over time due to motion, occlusions, random sampling, sensor noise, and lighting changes. So using this method, we can then track this bicyclist as it bikes by and accumulate the 3D points over time to build up a dense object model of this bicyclist. And here are some other object models that are built using the velocity estimates produced by our tracker. So in conclusion, I've worked on these three problems of velocity estimation, segmentation, and tracking. And for each of these problems, I've used this idea of modeling the causes behind an appearance change to give big improvements to our perception capabilities. I would like to acknowledge the help of my advisors, Sylvia Sabrise and Sebastian Thran, as well as the various people who I've collaborated with on these different projects. And finally, all in here, I think we might have time for one or two questions, and I can answer more questions at the poster session outside. Thank you.
Wow, that's perfect. So actually, we do have maybe time for one or two questions here. On the back?
So at Stanford, there was a method developed called RIF, R-I-F-F, or SIF, for finding key points in partially occluded objects that are invariant with motion. Have you used something like that to find your segments? I'm not sure what kinds of features you're actually using in the first step.
Right, great question. So normally what I do for most of my methods is I actually use the entire 3D point cloud of the tracked object rather than only looking at a small number of key points, just because sometimes an object will be so occluded that we can't afford to lose any information. But I have played around with some key point-based methods, and sometimes they can help in certain circumstances. So yeah.
Maybe if we can hold the question, we are trying to go to the next speaker. Sorry, we're trying to just make it on time. Okay, so next speaker is Amin Karaman he's with the Department of Electrical Engineering at Santa Cruz, and he's going to talk about graph-based framework for image restoration.
Okay, thanks everyone for coming. I'm a PhD candidate at University of California, Santa Cruz. I'm working under the supervision of Professor Milan, and I'm going to give a quick pitch on my research work on the graph-based framework for image restoration. So I'm going to start with the motivation of the work. So with the current cameras, handheld cameras that we have.
Can we take the time to fix the video mode on this laptop? Because I think if all the speakers are going to get that.
Yeah, unfortunately there's a problem. I have to fix this one. This laptop to that system always has this flicker. Today it happened to be much more than before. So probably next time we would use a different laptop. For today I think I don't have a solution.
Alex's didn't work through that, so.
Okay.
He's using a Mac.
All right. So yeah, with the existing handheld cameras, we usually observe some sort of degradation in the captured images in the form of noise or blur. And the goal of any restoration algorithm is to kind of remove those distortions from the input image. I mean, I'm showing one example that we're able to produce for motion blur, where the restoration algorithm is able to produce an enhanced output. So why graph-based methods? Graph representation is an effective way for describing the underlying structure of images. So the idea is to model any given image as a function on a graph whose vertices are image pixels, and the relationship between different pixels of the image can be described by a sort of appropriate kernel similarity function, which are the edges of that graph. So, for example, as an example, we have like image pixel I and pixel j in the image. You can model these two pixels as two nodes in the graph, which are connected via a weighted edge, and putting all these weights into a matrix, you will have a matrix known as kernel similarity matrix. This matrix, because containing the similarity information of the image, is able to encode the structural information of any given image, and therefore along with graph Laplacian matrix, is a very good tool for analyzing and representing images. So very quick, I'm gonna summarize the contributions of our work. So we have defined a new definition of graph Laplacian with performance advantages over previous definitions for image processing applications. We have used this new definition to develop a general framework for different restoration problems, including image denoising, image deblurring, which is able to produce high-quality outputs. For image deblurring, we have applied our algorithm to different sorts of blurs, including out-of-focus blur and motion blurs. Our framework is general in the sense that any other definition of graph Laplacian also can be described and can be used in our general framework and still produce very good results. But our framework is able to enhance over those previous works. As a separate work, we have used this similarity-based approach to develop a new sharpening algorithm based on the notion of difference of smoothing operators, data adaptive smoothing operators, which is able to produce state-of-the-art results for noisy and moderately blurred images. At the end, for the mathematical details, we don't have time. I would be happy to talk to you about the mathematical details and more examples in the poster session, but I'm going to show some more examples. For example, on the left, we have a blurry input image and the results of our algorithm. This is the motion blur, an example for out-of-focus blur, and the results of our algorithm. This is the noisy example for a color image and noisy example for a grayscale image. And this is an example for noisy and moderately blurred image that are the results of our algorithm. So we have published a number of papers based on our work. And yeah, that's it. Thank you very much.
So we are definitely time for a couple of questions.
For your out-of-focus